Okay, let's go ahead and get started. Hello class, this is Dr. Guo, recording the class from my home. Sorry that I cannot make to the class today, that because my wife is sick and she has appointment at a doctor's office, and I have to stay at home to babysit my twins, and which are very young, just half a year old. And so this is the first time I'm trying to record my class, and I think that's a pretty good try because I can break down the class into probably 20-minute segments, so that one period or one segment is not that long. Okay, let's first go ahead and review the highlight of the last week class. Starting from the last week, we have looked at demanded paging, and which is universal in the operating system design. And the key idea is based on paging, where the memory space for a process is broken down into pieces, and each piece is called a page. Okay, and so in other words, the storage of a process space is not contiguous, instead is non-contiguous. Okay, and the idea here is not all the pages for a process are needed for a time. Okay, and so basically only part of the pages for a process are needed, okay, at a certain time. Okay, and those unneeded pages will be stored on the disk, okay, and they will be loaded to the main memory when needed. Okay, so this will improve the capacity of the physical system, because we can take advantage of the storage space in the hard disk. Okay, so so the capacity of the system is not limited to the size of the physical memory space. Okay, so that being said, this incurs a event called a page fault event. Okay, which means, okay, when there is a logical address generated from the CPU, and the system queries the page table, but finds out that this page is not in the physical memory space. Okay, so the system has nothing to do but loading this page from the disk, okay, and to the main memory. Okay, and this is the flow chart we were looking at in the last week. Okay, and pretty much shows the sequence of actions that are taken to solve or to handle a page fault event. Okay, and first of all, there is an address coming from the CPU, and is an instruction, or is a reference to the main memory. Okay, and the first step is to query the page table. Okay, and the page number from the logical space is used as an index into this table. Okay, and the part of the page table is a flag. Okay, and this flag is either V or I, and the V means the wanted page is in the physical memory space, and when it's I, that means this invalid address, and the page is not in the physical memory space. Okay, and in this example, this flag says I, which means this page is not in the memory, is not in the physical memory space. Okay, and this would require an action of loading the missing page into the physical memory space. Okay, and if you recall from earlier chapter, and you should remember that when it comes to loading something from the I/O device, including the hard disk, okay, and the application program is not able to do it, okay, and your program has to be trapped into the operating system. So in other words, okay, and it's only the operating system that can handle this case, okay, this event, page fault event. Okay, so the operating system is going to put your program on waiting, okay, and while it's going to load the missing page into the physical memory space. Okay, and when there is a free frame in the physical memory space, okay, and the operating system is going to allocate this free frame to the requesting process, okay, and then it's going to reverse this valid bit. Okay, so this bit I will be converted to V. Okay, and once there is a free frame, in the physical memory space. Okay, so once that is done, okay, and this address in the page table is valid, okay, then it's going to restart the instruction. Okay, so here is the entire process of handling a page fault event. Okay, but there is a hidden concern that is between step 4 and 5. Okay, and step 4 says it brings in a the missing page, and step 5 says reset the page table. Okay, and these two steps can only be run when there is a free frame. Okay, and what if there's no free frame in the physical memory space? So in other words, all the frames in the physical memory space have been allocated. Okay, so in that case, okay, this sequence of actions is not reasonable. Okay, is not runnable. Okay, all right. So so when that happens, that deals with a decision. Okay, that is to choose a page from the physical memory that has already been allocated. Okay, and it's going to choose that as a victim. Okay, so the next topic in the nodes, the next major topic in the nodes is about the process of selecting a victim, okay, to be replaced. Okay, so this topic is a page replacement. Okay, and if you recall from the last class, okay, we were looking at this formula. This formula shows the concept of effective access time. So in other words, okay, when there is a memory request, okay, and this request may or may not incur a page fault. Okay, and if it doesn't, okay, and suppose p is the rate, is the page fault rate, okay, and the p% of time page fault happens, and 1 minus p is going to be the time page fault doesn't happen. Okay, so when page fault does happen, okay, and the effective time is going to be p times page fault time, pf. Okay, and in otherwise the effective time is going to be just the memory access time. Okay, so addition of these two terms is the effective memory access time. Okay, and after a simple manipulation, okay, and this formula can be translated to this one, which is ma plus p times pf minus ma. And again, ma is a memory access time, and pf is a page fault time. Okay, so as you can see that the effective memory access time is proportional to the page fault rate. Okay, so the higher the page fault rate is, okay, and the longer it takes to visit the memory. Okay, so this page replacement, under this topic, we're looking for a good way to lower p as much as possible. Okay, so lowering p will have a lower effective memory access time. Okay, all right. Okay, so here the page fault time in the previous example, okay, is the time for loading a missing page from the disk. Okay, so let's say that this it takes one disk visit to load the missing page. Okay, and so the page fault time is approximately the hard disk access time. Okay, the time for visiting the hard disk. Okay, and what can we do if the memory has no free frame and we're copying a page from the hard disk to the main memory? Okay, and the first two ideas are pretty punishing. Okay, and the first one is terminate the requesting process. Okay, so in other words, okay, you have one page in the hard disk, and when this page is wanted, okay, this process is done. Okay, and this is very punishing. All right, and another idea is to choose another process in the memory and swap out all its pages. So in other words, this process, one process needs a free frame from the physical memory. Okay, and when there's none, okay, and we have to swap up a entire process. Okay, so this is the punishing to the victim. Okay. Okay, and the last idea is the one that has been integrated in most of the operating system, which is instead of choosing one page, choosing one process to terminate or to swap up, why don't we just choose one page, okay, to swap up to the hard disk, okay, and for loading another page. Okay, so this is the most common solution, okay, and that's called a page replacement. Okay, and so here shows the concept of a page replacement. Okay, just choose one victim, one page victim. Okay, so and all the process and the whole process starts with the logical address finds a invalid record in the page table. Okay, and so suppose there's a request that comes in and wants this page record and whose flag says I. Okay, this I means invalid. Okay, so that means sorry, so this means the wanted page is not in the physical memory yet. Okay, so then the operating system will be invoked. Okay, and the operating system is going to come to the physical memory. Okay, if there is a free frame in the physical memory space, okay, the operating system is going to allocate it and assign to this record. Okay, suppose there's none, there's no free frame. Okay, the operating system is going to find a victim. Okay, and this victim, okay, has a frame in the physical memory. Okay, and suppose it's this blue one. Okay, this blue one is the chosen victim, and it has its page in the physical memory space. All right. Okay, and now this page need to go to the disk. Okay, and note the disk has a copy of the victim page, but it may be obsolete. So in other words, remember that under the managed paging, okay, the pages stay on the disk, okay, until needed. Okay, and when they are needed, they will be loaded from the disk to the memory space. Okay, so this blue page, okay, it was on the disk and it must have been loaded to the physical memory space. Okay, and after some time and some numbers and some information in this frame have been changed. Okay, so the data on the disk for this page has been obsolete. Okay, so then the operating system is going to flush the changes to the disk. That's the first thing we need to do. Okay, you choose a victim and you have to make sure the data for the victim is consistent on the disk. Okay, so as long as this is done, okay, and this space is allocatable. Okay, so then so step 3 is the operating system is going to find the missing page on the disk, okay, and then load it to the freed frame in the physical space. Okay, so once the missing page is loaded to the physical memory space, okay, and we have to update the page table. Okay, so this record is no longer valid, it will become invalid. Okay, and the frame number is going to be meaningless. Okay, and this record that used to have I means the address is invalid. Now it's going to become valid. Okay, and the -1, the frame number, okay, that was invalid, now it will be changed to F. Okay, so the next change is, okay, the bits are reversed for both pages. Okay, and the numbers are also flipped. Okay, all right, so that's the entire process of finding victims and saving the changes to the disk. Okay, and then load the missing page from the disk. Okay, so if you look at the interaction between the operating system and the disk, okay, there are two actions. Okay, and one action was, okay, and the flushing the changes in the victim to the disk. Okay, and another action is loading the missing page. Okay, so two actions. All right. Okay, so all right, so the last step is to restart the process. Okay, so once everything's done, okay, the victim is taken care of and the missing page is loaded. Okay, so this the requesting process can be restarted. All right. Okay, so here is the summary of this page for the service routine. Okay, in words. Okay, and step 1, find the location of the desired page on disk. Okay, step 2, find a frame, frame, and in the physical memory space. Okay, and so there will be 2 outcomes for at step 2. Outcome 1, there is a free frame, then use it. That's it. That's the end of the story. Okay. Otherwise, there's no free frame. Okay. In that case, the operating system needs to choose a victim using a page replacement algorithm, and then later we'll be looking at several algorithms for choosing a victim. Okay. Okay, so and if there's anything changed in the victim, okay, so in other words, its copy on the disk is obsolete, okay, and the operating system is going to visit the disk and in terms of writing the victim frame to the disk. So make sure no data is lost. Okay. Okay, so once the victim is taken care of, okay, and the operating system is going to read the desired page into the newly free frame, then it's going to update the page frame tables. Okay. Okay, and then it's going to restart the process. All right. Okay, so here and these 2 words, write and read, they are highlighted. Okay. And now let's take another look at these 2 actions. Okay, both actions are the interaction with the hard disk, okay, which is considered to be slow. Okay, and compared to the memory, the main memory access time. Okay, now let's look at the read. Okay, and it says read the desired page into the newly free frame. Okay, which is a must. Okay, and because the entire process is for making room for a new page, the desired page. Okay, but let's take a look at this action. Okay, it says write the victim page to the disk. Okay, and change the page and the frame tables accordingly. All right, so this action may not be that necessary. Okay, and we only need to do that when the victim has been changed. Okay, since it was loaded from the disk to the memory. Okay, so looking at these 2 actions, this is unavoidable. Okay, but this may be avoidable. Okay, depending on whether or not the free frame, the victim page has been modified. Okay. Okay, so now take a look at this formula again, and we were looking at this formula. Okay. And this formula says and in 1 minus p time, we just need to visit the memory, the physical memory space, because the wanted page is in the physical memory. Okay, and otherwise we need to visit the disk, okay, for the missing page. Okay, so now realizing that, okay, and when page fault does happen, okay, and there may not be a free frame. Okay, so in that situation, the operating system needs to take care of the victim. Okay, and the victim may need to be saved to the disk. Okay, which in the worst case scenario, which could incur 2 disk visits. Okay, all right. Okay, so and assume the victim is page P, and why was page P loaded in the memory in the first place? Because it was demanded by the process. Okay, and where was page P loaded from? From the disk. So in other words, page P, the victim, has its copy in the disk. Okay, and then what happened to the space for page P in the hard disk? Okay, nothing. Okay, it just stays there. Okay, and any changes to page P will happen in the main memory. Okay, so now page P is is selected to be the victim, okay, and it needs to be swapped out to the disk, okay, and this action is as discussed before, okay, this action, it may not be necessary if nothing in page P was changed since the last time it was loaded, okay. So it looks that we may be able to save one disk access, okay, in page replacement, okay, if the victim has nothing changed, okay. So here comes again this interaction between hardware and software, okay, and we want to know whether or not a page has been changed since the last time it was loaded, okay. And so a easy way of doing that is that we want to have a flag, okay, and every time this page is updated, is revised, okay, we want to set that flag, okay, and this is realized using a bit called a modify bit, okay. In many literatures and many contexts, this modify bit is often referred to as the dirty bit. Okay, so in other words, if the victim has been dirty, okay, and the information in the main memory is more updated than its copy on the disk, okay. So before swapping a page as a victim, the system should check the modify bit, okay, and if this bit is set, that means, okay, the operating system really needs to copy the page back to the disk, okay. If the bit is clear, there's no such action needed, okay. So, and this modify bit is really a software idea, okay, and but again, this modify bit or dirty bit, okay, has been used in many operating systems, okay. So Intel has this modify bit integrated in the page table, okay. So again, in this class we have looked at a lot of examples, okay, and the example shows one software concern or software solution, and then we can see a hardware realization, because the operating system is really the interaction between software and hardware, okay. So again, a modify bit is a software idea, okay, that keeps track of which pages have been modified, okay, and this bit has been integrated at hardware level, okay. Okay, and a similar idea applies to read-only pages, okay, and if a page is read-only, okay, and if this page is chosen to be the victim, okay, and then we can swap up, we can just allocate the victim page, okay, without the need to store this page back to the disk, because it's a read-only, it mustn't be modified, okay. So and if you remember from the earlier class, okay, a typical example of a read-only page is a page that saves instructions, okay, because most often instructions are not revisable, is not changeable, okay, they're read-only, okay. And let's see how much time we got. We have got 23 minutes. Okay, let's take a short break.